So this is the last case study we will do for this class. It's actually a very interesting case. It comes from, again, it's a Boeing crash. As we said, lots of things we learned from in fraction mechanics coming from some disastrous event. So in this case, I put a paper on the blackboard. So it's basically the person who did the investigation write down, and he actually developed a short course based on this, and to train engineers or practitioners to how to use fraction mechanics technique to do post-mortem analysis. And I think it's a very useful. It's a very informative article, so I post that, and I'm going to kind of go through that with the time we have in this class. So basically, this is it happened quite a long time ago in the 70s or 60s. So there's an airplane that was flying to somewhere in Africa, and right before landing, for landing, it put the stabilizer into a 50-degree flap. And then the recorder, the black box recorder, recorded a big noise, and people down below saw some big part fell off from that airplane, and then the airplane crashed, killed all 6 people on board. So then they had investigation, obviously, to trying to figure out why this has happened. So this, let me see. So what happened is, so this is the wing. Let me see whether I will show this. So this is the stabilizer in the back, and that is the cord. So the upper cord, middle cord, and the bottom cord, and that's what broke, and then the whole thing fell off. Of course, the plane lost control and hit the ground. So this is what looked like when they put the two broken parts together. So this is the part that connects to the airplane, and this is the other part that the stabilizer. And so it fractured, started over here, and it broke the whole thing. So the whole stabilizer fell off, and of course the airplane lost control. So the surface, we can look, basically this is look straight on the surface, and then we can see some things. We'll go into that in detail. So there's a website, actually, the FAA has an article or explaining what happened and all the design things, and what the surface look like, and how it happens, and all that stuff. So they have an interesting video here. I thought I pulled up. See, the sun was working before I put it.
The horizontal stabilizer on the Boeing 707 is a box with thin skins on the upper and lower surfaces and heavy spars on the forward and aft ends, identified as the front spar and the rear spar. The flight loads carried by the horizontal stabilizer result in downward loading on the structure. This downward loading on the stabilizer is reacted in 2 ways. First, the vertical loading is reacted at the attachment loads of both the front spar and the rear spar. Second, the downward loading on the stabilizer causes bending, putting the top cords of the spars in tension and the bottom cords of the spars in compression. The tension and compression of the spars is also reacted at the attachment loads of both the front spar and the rear spar. From this point forward, vertical loading will be omitted from the animation, so we can focus on the tension and compression loading of the reaction. To certify the original Boeing Model 707 stabilizer, the fail-safe capability of the structure was demonstrated by test. The test consisted of dynamically failing the attachment lug of the rear spar upper cord. This location was considered to be the most critical location for a structural failure in the stabilizer. The test successfully demonstrated that if a lug failure occurred on an aircraft in service, the flight loads could redistribute to the remaining intact stabilizer structure. The design of the Boeing 707-300 required a larger horizontal stabilizer that carried higher loads than its predecessors,
So
the
that's
Boeing
the one that
707-100 and 200. The center cord and attachment lug of the stabilizer design was added to carry fail-safe loads in the event of a failure of the upper or lower cord. To increase torsional stiffness of the 707-300 horizontal stabilizer structure, the lower surface aluminum skins were increased in thickness, and stainless steel plate replaced a portion of the upper surface aluminum skins. Normal flight loads of the horizontal stabilizer of the 707-300 are carried only in the upper and lower cords, much like the original two-cord stabilizer design of the earlier 707 models. No load is reacted by the center cord in normal conditions due to its location at the neutral axis of the spar and because the bolt is undersized in the lug attachment joint. To certify the horizontal stabilizer of the 707-300, it was assumed the structure would behave similarly to that of the 707-100. Specifically, once again it was assumed that the most likely and most critical failure would be at a rear spar attachment lug. The assumed fail-safe.
So you hear the person used assumed quite several times, right? And this is the same thing with the recent Boeing crash, is that you assume something and hope that happens. And a lot of time, disaster happens when you assume something, and that assumption is not correct.
For the new model 707-300 is that if a rear spar, upper or lower lug fails, the fail-safe center cord provides the load path for the load to be reacted at the center lug. This assumed failure scenario was substantiated by the manufacturer by analysis only. No new testing was required, and it was believed that the geometry...
So that is a flag. So they tested this for the Boeing 707-100 with two cord, and then they added the center one, that thinking that the center one will take the load if the top one breaks. But they only did analysis, they didn't do test.
The stabilizers of the 707-300 and 707-100 were similar enough to use the 707-100 test results to validate the assumptions made by the manufacturer. The in-service failure of the Dan Air stabilizer initiated outboard of the attachment lug. The cracking initiated at the 11th fastener, attaching the skin and stainless steel plate to the rear spar upper cord, a distance of about 11 inches outboard of the lug. The cracking at this location can be attributed to the addition of the stainless steel plate to the upper surface of the stabilizer. The stiff stainless steel plate attracted a higher amount of loading than the aluminum structure alone would have carried, and this high loading was transferred to the top cord of the rear spar through the fastener attachment. This higher than anticipated fastener loading led to crack initiation in the upper cord at the 11th fastener. The upper cord crack grew in fatigue over a period of 7,200 flight cycles through the upper cord. However, once the upper cord was fully fractured, the assumed redistribution of the loading to the center fail-safe cord did not occur. Because the crack location occurred outboard of the lug, the 11 inches of intact upper cord structure provided an unanticipated load path. Instead of the upper cord loads redistributing to the center cord and attachment lug, the load continued around the fracture location back into the upper cord. As the loading continued around the fracture to the upper lug, the length of the fracture grew. The upper cord separated from the upper web. The upper web then fractured diagonally. As the upper cord and web fractured, the center cord begins to pick up loading. However, the fracture continues to grow through the other components of the rear spar. The middle cord fracture occurred at the lug. Loss of the upper and middle cords resulted in overload of the lower cord. The stabilizer then separated from the fuselage, resulting in loss of control of the aircraft.
All right. So that's what. So the story of this is they made two design changes. Well, first of all, they have to have because the airplane is a different. Well, it's the same model, but it's actually take more load. So they changed the design. One is to add the middle cord to think that should add additional safety if the top cord breaks. The second part, the additional one, will take up the load. The second thing is they change. So during the flight test, they have figure out the rigidity, or the torsional rigidity of the stabilizer was not enough. So they replaced the aluminum panel with a stainless steel panel, which you think that stainless steel is more stronger, right? So we have seen this in our previous example, but the problem is because the cord should take more load than the original aluminum design. So the problem, of course, is with these design changes, they didn't do additional tests. And so they made the assumption, probably some engineers was very confident that it's going to work, and that didn't happen. So the story is actually, after this, they did the test on this to simulate the situation, and then they figured out that the assumption was completely wrong. The middle cord over here just was not able to take up the slack, and then they just fractured the whole part.